Here is where things get, admittedly, quite theoretical. Lore concerning water purification is scant at best, but real-world answers to the problem of cleaning irradiated water do exist. They aren't cheap, though, nor are they easy. But humans aren't so easy to count out. They're smarter than they give themselves credit for, more resourceful than they might think, and more ruthless than they'd like to admit. Reverse osmosis seems like the obvious choice to purify water of nucleotides. However, their construction and maintenance are above and beyond most factions. It seems reasonable to assume the humble water chip central to Fallout 1 is a part of a similar or more advanced reverse osmosis water purification system. Such purification plants also require vast quantities of electricity and advanced materials. As you can imagine, this makes such technology highly exclusive. So, let's delve into how a low-technology society could purify water of radiation in the best of faith possible. Otherwise, the point we are working towards is made immediately null by any dishonesty. I hope to be as faithful to lore, scientific accuracy, and realism as possible. I have done my level best to accurately research and correctly calculate the proportions, flow rate, and materials required for this process. If I have made any errors, they were not purposefully done, and I accordingly apologize. Let's begin, shall we? Removing radiation from water with limited to no access to electricity is an extremely difficult task, to say the least. I am by no means an expert, but my research has turned up one, albeit lengthy, method of removing radiation from water that isn't particularly advanced or requires electricity, a hard-won resource in the post-apocalypse. We also need to remember that we're not just dealing with the fallout from a worst-case scenario nuclear apocalypse, but the catastrophic failures of nuclear waste being improperly handled throughout the continent. There are repeat examples of pre-war America failing, downright neglecting, or outright refusing to deal with nuclear waste in an appropriate manner. This means that any and all problems with radiation are metastasized, and not just parallel to urban development. So, how do we deal with such catastrophic environmental damage? We can't, or at least not yet. For now, we can purify water enough that it is safe to drink. The following system is designed to process around 1,000 liters to 1,250 liters a day. No small feat. Don't worry, I have omitted the math of its construction, materials, and filters. I did spend 2 weeks working on it, but it takes an hour to explain. An hour you likely don't have. Therefore, I removed most of the math from the final script to save you time. So, let's get on with it. According to the U.S. National Academies of Sciences, Engineering, and Medicine, men must consume about 3.7 liters of water a day, and women must consume about 2.7 liters of water a day, assuming the average of 3.2 liters a day required per person. This setup could theoretically produce enough water for up to 390 people a day, if kept in perfect conditions. And it should be said that the larger the setup, the greater the volume of water purified. Furthermore, other water needs such as hygiene, crops, plumbing, or even just doing the dishes. I mean, a great deal more than 3.2 liters of water will be consumed a day. According to madeblue.org, the average American consumes, on average, 310 liters of water every day. It is impossible to know the exact amount of water any given individual will consume a day. So we will refer to the bare minimum needed for survival. For now, before the water even touches the first tank, a thick metal grate will help to keep out the majority of debris, which could damage the rest of the purification system. A sluice gate either side of the grate helps to regulate the flow of water and allow access to the grate area for cleaning, repair, and eventually replacement. These will be manual tasks. Separating the raw water reservoir or lake or river from the inlet tank is a fine mesh screen, after which the gravity-driven purification process can begin. Multiple slots are present for when a screen needs to be repaired or replaced without disrupting flow. What water that pools into the container beyond the fine mesh is considered prepared for the rest of the filtration system. The natural force of gravity is used to coax water throughout our purification system, thus ensuring no labor requirement and less moving parts for replacement. If the vertical space cannot be easily acquired, hand pumps can be used to move water to the top of the following step in the process. This does mean that the amount of manual labor required to work the plant increases exponentially with each pump, and every pair of hands is another mouth that needs feeding. Either way, a near constant flow of water to the top of Tank 1 is a necessity for every subsequent step to work. The first step involves the use of gravel, sand, charcoal, bone charcoal, and clay to filter out a myriad of contaminants. Each layer is contained within a separate tray, and all trays are kept inside of a tank, which we shall call Tank 1. Multiples of this process can be executed in parallel to each other. Tank 1 is a cylindrical unit, 1 meter in diameter and 1.5 meters tall. Each tray is also 1 meter in diameter and over 10 centimeters deep, with a 5 millimeter mesh base. Layers use multiple trays for ease of maintenance. There are 5 centimeter gaps between trays and overflow buffer spaces between each layer. The first layer consists of gravel, filtering 150 liters per hour. The purpose of this layer is to trap coarse sediments and larger particles, such as dirt and small rocks, to ensure a smooth water flow. The second layer consists of rough sand, filtering 118 liters per hour. The purpose of this layer is to filter medium-sized particles such as fine, silt, and organic matter to prepare the water for the slow sand layer. The third layer consists of slow sand, filtering at 50 liters per hour. The purpose of this layer is to absorb through natural microbial action. The fourth layer consists of activated carbon, filtering at 50 liters per hour. The purpose of this layer is to absorb impurities at the molecular level. This includes chemical, toxins, odors, and volatile organic compounds. The fifth layer consists of bone char, filtering at roughly 50 liters per hour. The purpose of this layer is to absorb heavy metals such as lead and cadmium, and absorb radionuclides such as cesium-137. The final sixth layer consists of fine sand, filtering at roughly 50 liters per hour. The purpose of this layer is to filter medium sand-sized particles, such as fine silt and organic matter. After passing through the filters in Tank 1, the water will drip onto a large clay basin placed underneath the tank. The basin is extra wide as a necessity, for its filtration rate is much slower than other mediums. Having a wide basin increases flow rate back up to 50 liters an hour, thus removing what should otherwise be quite a limiting bottleneck. However, water at the end of Tank 1 is still not safe to drink. Pathogens, residual volatile organic compounds, heavy metals, radionuclides, and inorganics may yet remain. Drinking this water would still make you very sick and eventually kill you. This is where the second step comes into play, on the next floor of our water purification plant. The second step involves the use of a zeolite tray and ceramic candle filters to remove cesium-137 and ammonia through ion exchange, while softening the water to improve the taste and reduce scaling. Any remaining bacteria and protozoa are also removed. The zeolite tray is 0.5 meters in diameter and 30 centimeters deep, with 1 to 2 millimeter granules, filtering at roughly 50 liters per hour. Each ceramic filter candle is about 10 centimeters long and 5 centimeters in diameter, arranged to connect to the above zeolite trays. Each one filters at roughly 3 liters per hour, so 20 of them mean 60 liters per hour, sufficient for Tank 1's 50 liters per hour output. The bottom 40 centimeters of Tank 2 serves as a collection area for filtered water, before it is piped at the base down to the next floor with a valve operation. Currently, the setup filters at 50 liters per hour. A lot has been removed from the water. However, there are still viruses, some more heavy metals, radionuclides, and inorganics that need to be removed from the irradiated water before it can be safely drunk. The third step, and ground floor of our water purification plant, is distillation. Either fire stills or solar stills are applicable here. Fire stills produce more distillate at a faster rate, but solar stills don't require combustibles. Considering that most of everything has been irradiated, the slower solar stills may be the better option, if for no other reason. That burning, irradiated wood will undo everything we've done so far, in terms of removing nucleotides from the water. However, solar stills also take considerably longer and require constant access to the sun. There are too many variables to get an exact number of liters per hour being distilled. From cloud cover, weather conditions, and construction materials, to how close to the equator it is. What can be known for certain is that solar stills are far less effective, and a great deal more solar stills than fire stills will need to be constructed to meet demand. This in turn means more materials, more labor, and more time spent on construction, to say nothing of the logistics involved in any of this. Multiple stills will probably need to be constructed to reach the desired 50 liters per hour. The specifics of each still differ with the type of still, quality of materials, and how large each still is. In other words, the construct's dimensions are the builder's choice, as long as there are enough of them to boil 50 liters per hour, or whatever your setup demands. The mass of wood needed to bring 100 liters of water to boiling point could be anywhere between 3 to 15 kilograms, depending on the quality of wood burned and the quality of the still itself. A continuous supply of wood will be required to keep the fire burning as well. So if you somehow find a source of radiation, clean combustibles, prepare for a constant flow of that material into your stills. Maybe you can build them to be heat efficient while you're at it. Or use electric heating elements. So far, the setup continues to filter at 50 liters per hour. Pathogens, heavy metals, radionuclides, and inorganics are now successfully removed from the water. However, despite being safe to drink, the water has been depleted of important minerals and will taste pretty bad. The last two steps are the least important, as the water is now clean and no longer irradiated. However, relying on demineralized water can cause long-term health issues, including, but not limited to, electrolyte imbalance, hyponatremia, hypokalemia, and hypocalcemia. These health issues can, however, be sidestepped by consuming mineralized water as often as demineralized water, so nothing too concerning. For the final step in this purification plant, we have the aeration tower and mineralization bed, filtered by a settling tank. The aeration tower adds oxygen and improves taste. It is 2 meters tall and 0.3 meters in diameter, filtering at roughly 50 liters per hour. The mineralization bed adds calcium and magnesium to make the water healthier to drink. The trough is 1 meter by 1 meter by 20 centimeters of limestone, clearly filtering over 50 liters per hour. The settling tank is used to settle out any particles of limestone dust that might possibly linger in the water. Finally, the water is totally pure and ready to drink straight from the tap, but is best kept in large, sterile containers which can be moved to wherever they are needed. This design can certainly be tampered with to be more efficient, but the general idea is solid. The main issue with purifying water is that the filters will need to be replaced over time and must be buried far away from any and all water sources. On top of everything else, tritium, which is an isotope of hydrogen, will still exist after all this. The best thing you can do is let the isotope decay for 12 years, as the water is kept in a secure, radiation-free storage facility. You can drink this water. It will not kill you, but it will raise your likelihood of getting cancer. So, it's a matter of just how desperate you are. Is a cup of water worth the month you'll lose? Even after all this, everything here needs to be constructed using materials that have not been affected by nuclear fallout. Considering that a minimum of tens of thousands of nuclear bombs dropped on America, the chances of finding unirradiated construction material is, well, extremely unlikely. But does it work? Yes. The setup on screen works just fine, if one can even build it. Could you build all of this? Most people can't. Even with a pre-war education, the likelihood that survivors of the Great War possess the knowledge and the skill to construct all of this is spectacularly low. Most probably aren't even literate. One would require access to an organized team of carpenters, metalworkers, masons, construction workers, plumbers, technicians, chemists, and mechanics. Unfortunately, it gets worse, of course. According to the lore, most people started looting the second they understood that law and order had broken down. This means that even more survivors are going to die, even after the bombs have dropped, by a combination of the desperate, the greedy, and the wantonly violent. So despite not being impossible to purify irradiated water, for most of us, it may as well be. By now, you're either fascinated by the theory crafting or wondering what it all means. This may seem like overthinking things, but understanding what nation-sized factions struggle to do will make what devastated families and isolated individuals are willing to do all the more poignant. And despite that, they may just die anyway. After all, even the rain is poison. The only safe place left to live would be a vault. But we'll get to that.